All right, good morning, everybody. My name is Peter Rizun, and the title of my talk today is An Introduction to Hardware Acceleration for Cryptocurrency. I have two main goals for this talk. The first is that you leave this talk thinking that specialized hardware is not only an interesting idea, but is in fact inevitable for things like faster signature validation and other computationally intensive tasks. My second goal is that you will reconsider whether Bitcoin's stacked base scripting system is worth keeping. At the end of my talk, I propose a RISC-V based alternative. So what do I mean when I say hardware acceleration? Well, by the word hardware, I mean some digital logic circuit designed to perform a specific computation. And by acceleration, I mean that by offloading that specific computation from a general purpose processor, we should see some gain, some acceleration in terms of speed, energy efficiency, or some other performance metric. To understand hardware acceleration, then, we need to understand, at least at a basic level, the building blocks of digital logic circuits. That brings me to part 1 of 6, the building blocks of digital logic. So this symbol here is, in my opinion, the most important element. It's a wire, and its behavior is very simple. If I apply 0 volts to the input, I get a 0 at the output. If I apply 1 to the input, I get 1 at the output. We can simulate this in Python as follows. It's a while loop that's always mapping the input to the output. Now in Python, it might take hundreds of instruction cycles for the input signal to propagate to the output signal. How long does it take in the hardware case? Now this actually stumps some of the software guys. So they might say that with a lot of work, maybe it could be as fast as 1 clock cycle. But that's totally wrong. It takes no work at all, and the signal propagates at the speed of light because it's literally just a wire. And this is one of the reasons hardware can be so fast, is you get this built-in while loop for free. This is a NOT gate. It inverts the input. So if the input is 1, the output is 0, and vice versa. This is an AND gate. Its output is 1 if all of the inputs are 1. An OR gate's output is 1 if any of the inputs are 1. This is a multiplexer or a MUX. It's like a switch. It routes either input 0 to the output or input 1 to the output, depending on the state of the select line. And all of these gates have that built-in while loop that I just discussed. The last element is called a flip-flop, and it's how we add memory. So the way it works is that the value sitting at the input gets saved to the output on the rising edge of the clock signal. Flip-flops are what allow us to add state to our digital electronic circuits. Together, these form a Turing complete set. What that means is that any computation that's possible can be performed by a suitable circuit made from just these 6 components. Bits versus words. Wires carry bits. Flip-flops store bits. A bus is a collection of wires. It carries a word. And words are stored in registers. Registers are just a bunch of bits all stacked up in a row. So part 2 of 6, a simple example of hardware acceleration. So this is a very famous circuit that's probably been replicated more times than any other circuit in the known universe. It is SHA-256. In particular, the part of SHA-256 is doing the 64 rounds of compression. So we have some AND gates here. We have some exclusive OR gates here. We have some adders. These are bit rotators. And these 1, 2, 3, 4, 5, 6, 7, 8 rectangles at the bottom, these are registers. So these are 32-bit registers. There's 8 of them, so 256 bits in total. And these are holding the hash value that we're slowly scrambling all the bits of. So what's really cool about SHA-256 and hardware is each round of the compression algorithm takes only 1 clock cycle. And that becomes obvious when you see the circuit, because like all these AND gates and all these XOR gates, they all have that built-in while loop. So they're always performing the computation. So the inputs are coming in from the registers, and they're doing all that computation basically like in time measured in picoseconds. And right here at the input of this first register, there's a value that's going to get saved into this register as soon as I turn on the clock. So I'll turn the clock on, and you can see this 48, 48, 48, 48. So it's just moving along every clock cycle. And as soon as the registers change, because they're wired directly to all these gates, the feedback term changes like in under a nanosecond, which allows us to move through the SHA-256 computation 1 round of compression per clock cycle. So we're going to be looking at these time area product graphs to visualize the improvements we get by offloading things to hardware. I have time on the horizontal axis in clock cycles. I have area on the vertical axis in a number of transistors. So I'm going to put a line right here at 1 because it takes our hardware circuit 1 clock cycle to perform 1 round of SHA-256 compression. Now let's look at solving the problem in software instead. So if I were to implement this in software, well, all of these registers are going to become variables. And then I'm going to have to and these 2 registers and save that to a temporary variable, and some more variables, and some more variables. Save all those and XOR them all together, do a bunch of summing, and basically build up the feedback terms instruction by instruction, and that's going to take many clock cycles. So I had Grok convert this to x86 assembly for me, and it solved the problem in 54 clock cycles. So this is the x86 assembly for 1 round of SHA-256 compression. It takes 54 instructions, 54 clock cycles. And the way this is executed is your operating system would set the program counter to the first instruction, turn on the machine, and then there it goes. 1 round of compression done. 2nd round through all the remaining 63 rounds. So come back to this diagram. In software, it takes 54 clock cycles, so we put a line here at 54. Now let's look at this axis, number of transistors. How many transistors does it take to build that hardware circuit for SHA-256? Well, on my diagram, I had a number of transistors column. So an AND gate, for instance, takes 6 transistors per bit. A flip-flop takes 16 transistors per bit. Those registers are 32 bits, so 32 times 16, and we have 8 of them. So you can add up all the transistors in that SHA-256 circuit, and it's about 20,000. So we color this square in purple. A modern x86 processor, like a 64-bit x86 processor on a Skookum desktop, has 100 million transistors per core. So how much smaller this rectangle is represents the gain we get by offloading to hardware. So we are 250,000 times better than software. So I think it should be obvious to people why faster is better, but why is fewer transistors better? Well, fewer transistors better because if you're going to spend 100 million transistors, well, you could just replicate this circuit 5,000 times and have 5,000 SHA circuits running in parallel. So time counts, but also number of transistors counts, and it's a product that matters. So people hear something like a 250,000 time improvement, and they think that's crazy. That doesn't make sense. But this is already played out in Bitcoin mining. For instance, when Satoshi released the original Bitcoin client, it had a CPU miner, and it could do about 100,000 hashes for every joule of electrical energy. Today's best ASICs can do about 60 billion hashes for that same joule of electrical energy. So there's been a 600,000 time improvement in our ability to do SHA-256. And that's almost entirely due to this gain you can get by making custom circuits to perform a specific computation. So part 3 of 6, accelerating digital signature verification. So nowadays we have fantastic ASICs for doing SHA-256. Unfortunately, that doesn't help us to scale Bitcoin because digital signature verification is the computational bottleneck, not hashing. To get an idea of how much of a bottleneck it is, we're going to consider this global adoption scenario where we imagine we have 5 billion people. They're making 2 transactions per day, so 10 billion transactions per day in total, for about 100,000 transactions per second sustained. Now, we want to have hardware that can easily keep up. So, we want to have lots of headroom. So, I think we want about, 1 to 10 million signature checks per second. A modern processor can do about 20,000 signature checks per second per core, so 50 microseconds per check. So a 64-core machine, like a Skookum desktop machine you might pay $10,000 for, is already able to keep up to the lower end of the digital adoption range, of the global adoption range. But I don't like running Bitcoin on my main desktop machine, and especially if it was bogging down all 64 cores and my fans are blazing and my office is heating up. I want to run Bitcoin on a tiny little node that I plug into my router and I just SSH into it when I need to. And to do that, we need to build a digital logic circuit to carry out the signature verifications more efficiently. Okay, so let's visualize what that hardware solution might look like. The hard part of signature verification is doing what's called elliptic curve point scalar multiplication. So you have these curve points, an x and a y coordinate. The both coordinates are 256-bit numbers, and you're doing this kind of crazy remapping procedure to calculate a new point. And the circuit to carry out that is much larger and more complex than the circuit for SHA-256. It would take a whole talk for me to explain that circuit to you. But the heart of the circuit is very simple. It's just a ginormous 256 by 256-bit modular multiplier that's built with millions of transistors. So it just takes two numbers, A and B, multiplies them together, and returns the product modulo Bitcoin special prime. So that's the heart of the verification circuit. And because we've invested so many transistors, millions of transistors building it, we need to keep that machine busy. So you can imagine the rest of the circuit is you have these two workers up here, and their job is to feed 256-bit numbers into that machine every clock cycle. We have another worker down here. He's catching these 256-bit products as they come out, and they're coming out fast, like every nanosecond. We have workers over here, and they grab some of those numbers. They might double some, they might add some. They perform a simple computation, and their job is to send those numbers back to the feeders at the right time in the sequence to carry out this algorithm. And if you organize your workers just right, which means if you design the supporting hardware circuit just right, you can carry out the signature check in about 5,000 clock cycles. At 1 gigahertz, that works out to about 5 microseconds. And it takes about 5 million transistors to do this. So coming back to our time area charts, for the x86 processor, it takes about 50 microseconds to do a sig check. Our solution takes 5 microseconds, so we're 10 times faster. And 5 million transistors instead of 100 million, 20 times smaller, for about a 200-time improvement. So not nearly as much as hashing, but still pretty impressive, as we'll see on the next slide. So it turns out that we can verify all the world's transactions on the head of a pin. And so here we have a pin, and we're going to assume the head has an area of 1 millimeter squared. So how many transistors fit in 1 square millimeter of silicon? We'll assume TSMC's 5 nanometer process, so a pretty new modern process that miners are actually using today. So lower your hand if you think this doesn't apply. So like 1,000, who thinks 1,000 transistors fit in a millimeter squared? Put your hand up if you agree. Okay, yeah, it totally does. Put your hand down when I say number too high. What about 10,000? Do you think 10,000 fit? 100,000? A million? I'll just put my hand. I don't want to confuse you guys. 10 million? 100 million? A billion? Okay, a billion doesn't fit, but 170 million transistors fit on a pinhead with TSMC's 5 nanometer process. So it's incredible. Everyone had their hand down before that. So that means we can fit 34 of those verifier cores onto our pinhead. Each core can do about 200,000 sig checks per second. So that's 6.8 million sig checks per second per pinhead die. How much do those pinheads cost? Well, you have to pay TSMC about $18,000 to make a wafer full of ASICs. So these are 300 millimeter diameter wafers, like wafers they're about a foot in diameter. You slice them up to get your chips out. So a wafer gives you about 50,000 of these pinheads. So each chip, the silicon in it costs about 36 cents. So 1 millimeter, 36 cents, all of the world's transactions being verified. It's pretty cool. So, I mean, there's obviously some costs I haven't encountered. There's millions of dollars of engineering that go into that. And making your first wafer is very expensive because you got to dial in the process and build all the masks. But once you're up and running, the incremental cost is really quite affordable. So what I learned from this is that at scale, compute will not be a bottleneck in terms of cost, energy, or size. Instead, the bottleneck becomes access to state, like the UTXO set, but that's a discussion for a different talk. So part 4 of 6, the Blitz accelerator card. So this is not just an idea. We've actually built a signature accelerator. We call it Blitz, and I have a picture of it right here. It uses an FPGA rather than ASIC as a starting point, and that's pretty normal. Normally you use an FPGA to prove your design before you go on to fab an ASIC. An FPGA, it's like a reconfigurable ASIC. It stands for Field Programmable Gate Array. And what you do is you describe your circuit in a hardware description language like Verilog, and then you use the FPGA toolchain to synthesize that circuit onto the chip. So it's not like the FPGA like simulates your circuit in software. It actually like rewires itself to become the circuit that you described. So this thing plugs into the M.2 slot on your motherboard and connects via PCIe. Preliminary numbers look like we'll get about 200,000 SIG checks per second, 3 watts of power. It's a lot less than the ASIC I talked about because I can only fit 5 cores instead of 34 cores, and my clock's running a lot slower than I assume for the ASIC. But it's still impressive. Okay, so how does Blitz connect to your computer? The answer is through the magic of PCIe and memory mapped I/O. So we got a diagram of Blitz here. The purple square is the heart, the signature verifier cores. So Blitz has an input register that the user would write the signature they want checked, signature, pub key, signing hash, and it exposes an output register where it writes the pass-fail result. And your computer that's connected to, well, it has some memory map. So typically your RAM might be from addresses 0 to 7FFF. So this is a 2 gigabyte machine. And above that, you have address space reserved for memory mapped I/O. So these are all the registers for the devices that are attached to your computer. And Blitz just becomes one of those devices. So the way it works is when your computer boots up, the PCIe subsystem scans all the devices. It sees Blitz. It says, okay, Blitz has this input register, it's 164 bytes. I'm going to map that over here to address 9000000, and I'm going to map the output register to address 9000100. So this is really cool because from your computer's perspective, it doesn't know that it's talking to Blitz. It can't tell the difference between Blitz's registers and just plain old memory. So if you want to check a SIG in C, you might have your signature you want checked in a character array. So you just mem copy that to Blitz's input register. And then to read the result, you just dereference a pointer to Blitz's output register, and you get your pass-fail result. If you read it before the result's ready, the timing is taken care of behind the scenes through the PCIe subsystem. Just like if you're trying to dereference some memory from RAM and you had a cache miss, it just takes a bit longer. So the timing is totally transparent to the user, which is really cool. So of course, a modern operating system won't let you poke around physical memory. So in user space, access to Blitz is facilitated through a kernel driver. That makes it even easier. So a user process connects to the kernel driver. Blitz looks like a file. So here's the Python code for checking a signature in Blitz. You would import the OS library. You'd open the dev Blitz file in read-write mode to get your file handle. To that file handle, you would write the signature, pub key, and signing hash. And then you just read a byte from the same file. And if it's 1, it means the signature is valid. 0, signature is not valid. So it's super simple in user space. And what's cool is you can have multiple user space processes running in parallel, and they can all have Blitz open and making signature requests at the same time. And it's the kernel driver's job, along with Blitz's input FIFO, that manages all that all these race conditions. So the kernel driver is always listening to all the user space processes making requests. It sends those all to Blitz, it receives the results back, and it makes sure it sends the pass-fail result to the right calling process. And that all happens transparently. So from the user process, it's all very straightforward. We hope to make a Blitz experimenters kits available in the summer so people can start playing around with this. Okay, part 5 of 6, validating transactions in hardware. So we validated, so we did SHA-256 in hardware. We talked about checking signatures. Well, we can validate entire transactions in hardware too. Let's just review some transaction mechanics. So this is a picture from Satoshi's white paper. We'll assume this transaction has been mined into the blockchain. So Alice owes a coin at this point. Alice wants to send this coin to Bob. What does she do? Well, she needs Bob's public key. She takes the coin ID, the ID of the coin she wants to spend. She hashes it with Bob's PubSec key. She takes out her signature, her private key, and she signs that hash. She packages all that up in a transaction, and she broadcasts it to the network, or she delivers it to Bob. So the transaction contains the ID of the coin being spent, Bob's public key, and Alice's signature. It doesn't contain Alice's pub key, and it doesn't contain the hash that was signed because any node on the network can figure that out locally. So that's how a transaction is signed. Now let's look at how a transaction is validated. So that transaction comes into our node, enters a validation engine. And the first thing our node does is it says, okay, this transaction is trying to spend this coin. Does it exist? Is it unspent? So it goes up into its UTXO set. It says, okay, that coin does exist, it's unspent, and it belongs to Alice. So it plops Alice's pub key here. It appends it to the transaction. And then it says, well, I need to check Alice's signature, so I need to compare it against the hash that she would have signed. So it hashes the ID of Bob's public key to get the signing hash. And now it has enough information to check the signature. So this is basically Blitz's input register. So we just write this to Blitz, get the pass-fail result back. And if it's good, then the signature goes green, enters mempool, and we return the coin to the UTXO set, this time with Bob's public key and a new coin ID, obviously. So this is all really easy to do in hardware. And this is how Bitcoin transactions work in the white paper, but the way Satoshi actually made them work is a lot more complicated. There's this Bitcoin script system and this stack machine that allows you to give programmable restrictions on when a coin can be spent. So I was trying to make a physical Bitcoin machine, like physically implement the stack and all the opcodes and hardware, but it turned into a really big mess. But in that process, I had an idea that I want to share with you now. And Vitalik Buterin, it seems like he had the same idea in parallel. And that is to use RISC-V instead of the Bitcoin virtual machine or the Ethereum virtual machine. So part 6 of 6 is RISC-V and memory mapped transactions. So here's where we're at. We had the transaction here in white. And when we started validating it, we pulled the pub key from the UTXO set. We calculated the signing hash, and then we do our stuff to check all this. In RISC-V, the script pub keys become pub key programs. So this thing we would pull from the UTXO set would now be a RISC-V assembly program that describes the spending conditions for the coin. So the critical observation to make, the critical insight, is that the entire transaction and all this appended data can become the RISC-V machine's address space. So this is address 0 out to address maybe 1 megabyte or so. So the RISC-V machine can just start running its program and operating on every byte of data in this address space. So that seems very abstract, so we're going to make that really concrete with an example. I call it silly sig, and it's a totally insecure signature scheme. We're going to imagine we have 32-bit signatures, 32-bit pub keys, and a transaction is valid if the signature XORed with the pub key is all ones in binary, 0x, FFF, F, FFFFF. Okay, here is the RISC-V program that would check that. Don't worry about trying to understand it. We're going to go through it step by step. This is what it looks like assembled in hex. So this is the thing that would be sitting in the transaction in hex that would get pulled into this purple area. But because RISC-V instructions are all 32 bits long exactly, we can imagine the assembly code is just listed here. So each line is a different line of assembly code. So the validation engine pulls the RISC-V assembly into the transaction space, and it sets the RISC-V machine's program counter to the first instruction. And that's load word to the T0 register, the data at address 64. Address 64 contains Alice's signature, which is this number. So this number gets loaded into the T0 register. Next, I carry out this instruction, which is to load an immediate value, dead beef, this is the pub key, to the T1 register. Now load immediates take two clock cycles to play out, so it takes 2 clock cycles, and now dead beef is sitting in the T1 register. Then we XOR T0 with T1 and store the result in T2, which indeed does XOR to all Fs, or all ones and binaries. And then we load the T3 register with -1, and -1 is just FFFFF. It's just a quick way of writing FFFFF. And then we get to this branch instruction. So this BEQ is branch if equal. So if T2 equals T3, so if T2 equals T3 and they are equal, then it's going to add 8 to the program counter. So this program counter increments by 8, and it skips over the mark invalid. It hits the mark valid instruction, and it makes the transaction go green, and it enters mempool as normal, and then the RISC-V machine resets for the next cycle. So it's almost the same as what's happening now. The difference is being we're using RISC-V assembly instructions instead of Bitcoin script, and instead of a stack to store our data, we have registers. I had 4 here, but the RISC machine actually has 32, and we can also store data to all the free address space this left over in our little scratchpad area here. Okay, there's some cool things you get automatically. For instance, you get native transaction introspection. So RISC-V's load word instruction copies a word from anywhere in the address space to the specified register. So I was doing transaction introspection right here. I loaded the signature into my machine's memory. So I can load any word from anywhere here into memory. You get linear memory for storage. So RISC-V has a store word instruction that writes a word from a register into the memory space. So if I went store word T2, 132, that's going to store whatever's in the T2 register to this empty spot in memory right here. So I can use all this as like a scratch pad for my computations. RISC-V is Turing complete, so it does loops. So here's a simple example of counting to 1,000,000 in the RISC-V. Because it can do loops, there's the halting problem. We don't know in general whether a program will ever stop. So we need a way to resolve that. So the mechanism here is called pause. So if the transaction validation engine thinks a program is taking too long, it can just pause it, and it does that by basically stopping the clock to the RISC-V machine. And then it copies all the values in the 32 registers and the program counter into a register file that it appends, that it prepends to the transaction. And any of the allocated memory that's been used is at the end of the transaction. And then this binary blob moves through the node as an atomic object. So this is like a transaction that contains its own execution environment. So that might enter like a retry queue for trying it again later, the same way that a transaction would enter a retry queue if one of the inputs were missing. Other RISC-V benefits, we have function calls. So there's a jump and link instruction that would allow execution to jump to imported code, for example, from a read-only UTXO and then return. So one example is you might want to implement a quantum-resistant signature scheme, and maybe that takes 20 kilobytes of assembly instructions. But I don't want to have 20 kilobyte transactions, so we can just write that once to a read-only UTXO, and then transactions, rather than including all 20 kilobytes, they can just reference that UTXO, and then execution can jump the program written in that UTXO. So that's pretty cool because it basically allows for all the sorts of permissionless innovation. Indirect addresses, that's kind of confusing. I'm not going to talk about that. Compiler support. This is a standard RISC-V machine with standard memory addressing. It's just linear addressing. So any C compiler that can compile for RISC-V can compile C programs to the programs you would need for this system. It's a simple physical machine. A lot of people think this is some crazy science project, but you can implement RISC-V with 40,000 transistors. Implementing the Bitcoin virtual machine or the Ethereum virtual machine is way harder. So this is actually simpler in hardware than what we're doing now. We'd probably want to have a fast multiplier, so maybe it would take it to 120,000 transistors, but it's still very small. Permissionless innovation, no more bickering over new opcodes, because you can do anything you want already because you have a Turing-complete language. It just has full access to the transaction data. And then the other point is hardware acceleratable functions. So you might have a function that gains widespread use. Everyone agrees it's useful, like that new quantum signature scheme. So if everyone's calling that same function that runs 20 kilobytes of RISC-V assembly, well, we can optimize that and create like a secondary hardware path that computes that more efficiently in the future. And that doesn't require a soft fork or a hard fork. It's just an optimization. Some RISC-V concerns. There's a resource exhaustion. For instance, you need some way to limit max clock cycles, like a gas or some other mechanism. So this is like a solved problem now, I would say. Memory, that's already solved because you just have a physical 1 megabyte of memory. If a smart contract accesses more, it's invalid. So those are, I think, fairly easy to fix. Everything is writable by default. So the program could technically rewrite outputs, which you don't want in most cases, but so we'd have to have some safeguards against that. But maybe there are some applications where it would be useful to rewrite outputs dynamically. So we need to give that some thought. And lastly, it's a huge change. Like, this is a completely different way of thinking about cryptocurrency smart contracts. But I believe if Satoshi could do it again, he would pick something like this because it actually is simpler. Okay, so my goals for the talk. So have I left you thinking that specialized hardware is inevitable? I hope the answer is yes. And are you considering whether Bitcoin's stack-based crypto system is worth keeping? I think that's a harder sell, so let's just think about it. Okay, so that's my talk. Thank you.
All right, I can see we've already got our first question over here. This one better be good.
Is there a certified compiler available for RISC-V architecture, completely certified if possible, if at least partially?
When you say certified,
like formally verified, like C has CompCert, right?
Yeah, I believe so. Like the RISC-V community is really strong, and they actually have there's a whole formal validation framework in existence for so new people can make their own new implementations of RISC-V and formally validate against the specification. So I assume the same things exist for compilers.
So the benefit, right now, Bitcoin stack programming languages, I would say partially verified. There have been some attempts and whatever. Moving to this instruction set would be beneficial because everybody would be working
Yeah, in the context of formal validation, this is way easier because it's RISC-V is used everywhere now, and there's huge efforts to make that consistent. So it's way easier to formalize a RISC-V implementation than Bitcoin.
Right. So that would be a benefit for because there could be some issue with Bitcoin stack programming language, and once Bitcoin becomes more popular, way more, it would be worth for people to find out what the issues with this are. So in a way, migration would not just be performance improvement, but it also tapping into all the safety issues and or safety benefits which the RISC-V community will bring.
Exactly, they've already solved most of those problems for us. We're just using a standard register machine at that point.
Awesome. That's That's very cool. Again, I really love the presentation.
All right.
How do you see the upgrade path going? Like, let's say in some distant future, there really is a market need to like accelerate every aspect, including the scripting language, or like, at some point, I mean, I would imagine you'd have to support both. You support the old fourth language and then the new thing. I mean, do you incentivize the new thing with like a discount, or do you? How would that even work? I haven't thought about how the upgrade path would, like, how do you get people on the new system?
Yeah, I think it's yes. I mean, if you're developing a new coin from scratch, it's a lot easier. But I think you probably just run both virtual machines in parallel, and just have a different transaction, like a transaction format. But well, I think they would, just because they can do more things or something. Yeah, I think if it's true that it's more powerful, then I think the adoption would happen organically. Because I think a lot of people would, like, if you could, like right now, if you wanted to write a quantum resistant signature scheme for Bitcoin Cash, it would have to go through at least some software fork process. But this way, you could just do it permissionlessly, and you could prove it out in the wild.
Or you might be able to do it after all the upgrades that we have proposed in 2026, but it would be like this huge. It would be like a huge script.
That is true. Yeah.
So you might with this, it might be just so.
Yeah, I was having some data with some BCH guys. Yeah, it's true. If you at the computational level, yeah, the scripting language with a big stack can do everything the RISC-V can do, but like you said, it's going to be harder to even navigate that. Where RISC-V, you can just write your algorithm in C and compile it.
I have a question.
Yeah.
That Blitz card you have, where do I send my BCH so we can get some into the hands of Kalen?
Sorry, I missed that.
He's just saying you want to link up the two of you, and let's get this innovation cracking.
Okay,
all right.
Let's do it.
I have one, so you can implement it, so I can buy one after and use it.
Okay.
Okay, amazing.
Hey, so part of the Bitcoin lore is that the specialized hardware for mining is not a problem, because in case the government decided to attack us, we could just go back to consumer hardware for the mining, go into hiding. So the question is, do you think we are going to need this only after we reach such massive adoption that the risk of government attack is very small, or do you think we're perhaps going to need the hardware accelerations even
Well,
before?
so I mean, like, I think it's not like we're relying on, it is specialized hardware, but it can be open source in our community, right? And we can implement that on an FPGA, on different ASICs, so it can still be very decentralized. And in fact, I think it would lead to a healthier ecosystem, because right now we're dependent on Intel, like we're trusting Intel, we're trusting other hardware. If we had our own hardware, that's more trust that we remove. So I see what you're saying, but I kind of view it the opposite. I think it actually adds decentralization.
What does it mean to write or rewrite outputs? So you talked about a transaction rewriting other outputs. Does that mean that the semantics or the spend as seen in the transaction statically is actually changed by the execution?
Right, because so this is the entire transaction, and in this case, so Bob's public key here. So this is basically the output. So I don't have values. There would normally be a value attached. But what I mean is, because the whole transaction exists in the execution environment of the RISC-V machine, it can technically change the bits of that output, which would make the transaction valid. So you'd have to check. But what I'm saying is, you typically wouldn't want that. So you can have some safety mechanisms to prevent certain areas in your transaction from being overwritten. But my point is that maybe there are some cases that we haven't thought of yet where it's actually useful to overwrite some of the outputs, because there's different sig hashes where you actually allow outputs to be changed, right? So with a sig hash none flag, you're basically saying, I don't care if the output's changed. So in that case, maybe the virtual machine can write the output. So maybe there's some cool application no one's thought of.
Okay, I have a question, which is, you mentioned Vitalik also brought this up recently, and caused quite a stir, because, like you say, it's a huge change, and for Ethereum it's actually even bigger than BCH due to their relative size. Of course, smaller coins, and maybe Nexa is in this camp. are already able to move on to this stuff more agilely, and somebody will start a new blockchain with this as their concept as well too, right? So what do you make of the industry trend in this direction? Do you think in 5 years, 10 years, this will just be completely standard? Do you think there's still room for the existing models, or how are the bigger ones going to adapt?
I don't know. I mean, like, as soon as this hit me, I'm like, it seems to me that this is the inevitable future. But maybe we were only starting to kind of throw around this idea. I thought it was really cool how I read Vitalik's thing after I had a study. I'm like, oh my God, he's thinking the same thing I am. So maybe we're onto something. But maybe, in a couple of months we'll realize that this doesn't work as well as we think it works. But from where I sit today, I see this as the future of crypto. I think it makes sense to have a RISC-V machine in all currencies. So I think this will just become a standard.
Yes, and then probably in parallel, like you said, and then the idea would be organically people transition one to the other, and eventually would you even want to deprecate the Bitcoin script, or would you always keep that around?
I think what you do is you'd eventually you'd deprecate the Bitcoin script machine,
Yes.
or the virtual machine, but you would kind of emulate it in RISC-V.
Yeah. Makes sense. All right, any more questions? Oh, at the back here.
So I went to that statement you had on the last slide, Nexa. Can you talk a little bit about that?
Oh yeah, so Nexa is a cryptocurrency that we launched to kind of explore these different aspects of cryptocurrency that we want. We don't have RISC-V running on it yet. We've added registers. So right now our scripting language is very similar to BCH, but we've added some registers, and RISC-V is just an idea that doesn't exist yet on Nexa. But what I think is really cool about Nexa is Nexa's proof of work. So what the miners do in Nexa is they do the same computations that you need to do to verify a transaction. So Nexa POW is basically doing elliptic curve point multiplication and UTXO lookups. So to be a good Nexa miner, you have to develop the hardware, the same hardware that we need to solve the computational bottlenecks of scaling cryptocurrency in general. And that was my biggest motivation for working on that project.